Welcome, dear students, to another session of online classes. In the previous class, we have already finished with the introduction to the alkene, the orbital structure of alkene, and the nomenclature of alkene, which includes common system of nomenclature followed by IUPAC system of nomenclature. In the current session, we are going to study about the isomerism seen in alkenes, along with few method of preparation of alkenes and few characteristic reactions seen in alkenes. So we'll start up now with the isomerism in alkenes. What is isomerism? Isomerism is a phenomenon in which compound has same molecular formula but show different physical and chemical properties. That is due to difference in the arrangement of atoms. So we have seen in alkanes that structural isomerism has five types. Those were chain, positional, functional, tautomerism, metamerism. Focusing now in alkenes, alkenes starts with ethene or ethylene, followed by propene, followed by butene. We are going to compare these three structures. In the text, what we have sent you the document of a textbook, which says that uh, ethylene, that is ethene, and propylene, that is propene, have no structural isomers. So what is structural isomers? A structural isomerism of following types. There is chain, positional, functional, tautomerism, and metamerism. Are they showing this five types at least? If they are not, then they don't show structural isomerism. So what is the structure of ethene? The structure of ethene is C double bond. See, it can accommodate two more hydrogen. This can accommodate two more hydrogens. This is another. The name is ethylene. If I try to number it, 1, 2. First position is for the double bond. If I write one more structure, C double bond C with H2 and H2, and I number from this side, left side, even this structure also has first position to double bond. So even here the name is ethene. It can also be written as eth, one ene, or one hyphen ethene. This is how it is named using IUPAC nomenclature. So it doesn't show, there is no evidence of any structural isomerism in ethene. What about propene? Propene has the structure carbon carbon double bond carbon. I have to write here H2 and here H and here H3. I have to number from left side so that the least number should be given to the double bond. Here the name is prop, one ene or one propene. If I write one more structure with double bond here, then this will be CH2, H, H3. If I number from here 1, 2, 3, why I have to number from the left side? Because it will get the least possible number. I cannot number from here 1, 2, 3. This one is from, because it will give second position to the double bond. So even in this case also it is one propene. So there is no evidence of any structural isomerism in this structure. In case of butene, there is a different scenario. We'll try to. So there is no evidence of structural isomerism in case of ethene and propene. The other name of ethene is ethylene. Propene, other name is propylene. Right. Moving on to the structure of butene. Now butene has four carbons with one double bond here. If it is here, I have to number from the right side 1, 2, 3, 4. I cannot number from here 1, 2, 3, 4 because it is giving third position. So this number is wrong. Here it is giving first position. This one is correct. The name is 1 butene. The other scenario is 1, 2, 3, 4. Double bond he is here. It is CH3. This one is CH, CH, CH3. This is 1, 2, 3, 4. a number from here, 1, 2, 3, 4, second position. So this one is now 2-butene. So this one butene and 2-butene are example for structural isomerism. Specifically, it is showing positional isomerism. It is showing structural isomerism in which it is nothing of which type it is positional isomerism. We can also have one more case in case of butane, that is 1, 2, 3, 4. This one is CH3, CH2, CH3. This carbon cannot be added any hydrogen because 1, 2, 3, 4, all the valencies are satisfied. In this case, the name of the compound will be 2-methyl propene. Because it is at first position, I am not writing the position, 1-propene. 2-methyl propene. Even this is also an example of structural isomerism wherein it is positional isomerism. So now what is important here is the molecular formula, is it same or not in all the cases. This one is having 1, 2, 2, 3, 4. 4 carbons, C4, hydrogens are 3 plus 3, 6, 7, 8. Count here also it is C4H8. Even here also it is C4H8. So due to difference in the position of double bonds, which is leading to a formation of an isomerism that is by name structural isomerism of type positional isomerism, they show different physical properties and sometimes chemical properties also. So propene and ethene or ethylene or propylene is not showing isomerism, whereas butene, that is 1-butene, 2-butene and 2-methyl propene, which is IUPAC name of this compound, this 2-methyl propene, shows which isomerism is structural isomerism or which type positional isomerism. The other name of this compound 2-methyl propene is isobutylene. We have seen this example when we have seen in our previous video of nomenclature, that is specifically common system of nomenclature. The other aspect what we are going to study here is we need to understand one thing, that in ethane the structure was carbon-carbon having 3 hydrogens, or it can be one CH3 group also. So what is the name of this compound? It's 1, 2, 3, 4. It is butane. If I see one more example, carbon-carbon having 3 hydrogens. This one is ethane. And all are having sigma bonds. This all bonds are sigma bonds. We have seen the orbital structure, how the sigma bonds are formed. We have already studied in detail in those videos. So in butane and ethane, there are sigma bonds. You need to remember that the basic difference between alkene and alkene is, in alkene you have single bond, those are sigma bond, and in alkene you have double bond. Then this one is pi and this one is sigma. There is one more possibility also, it can be R, CH, double bond CH, R. R can be any alkyl group. So what we were discussing here is, in case of alkanes and alkenes, the basic difference here was that alkanes had sigma bonds and alkenes have pi bonds. The presence of pi bonds has certain role, and due to that presence of pi bond, it is giving rise to a phenomenon called as geometrical isomerism. So where is the presence of pi bond. The pi bonds are present in case of alkenes, and due to this pi bond, there is a phenomenon seen in alkenes that goes by name of geometrical isomerism. In geometrical isomerism, what happens is, I put this one first. Right. There is restriction in rotation of the compound. You know, the three-dimensional structure of any compound, there is rotation of compounds. When there are sigma bonds, the rotations are like it will stay in the same position. For example, you have this compound which is RCH2 CH2R. Now what happens usually is, when there is presence of only sigma bond in this compound, the rotation of compounds take place, and this might be written as R C H H C H H R. So the rotation, that means that if this is for identification R1 and R2, it will rotate completely, and this one will be R2 and R1 when there is rotation of compound. This is case when there is sigma bond present. But in case of RCH double bond CHR, that is an example of alkene. This one is 1, this one is 2. Presence of pi bond prevents the free rotation of the double bond. So first thing to remember, double bond is present, rotation will happen, but due to the presence of pi bond, there is restricted rotation. This restricted rotation or prevention in rotation around carbon-carbon double bond is giving rise to a phenomenon by name geometrical isomerism. The example is very simple, that is, carbon has this two bonds here, which one is pi and sigma. Here you will have R2, R1, hydrogen, hydrogen. The other scenario is carbon having double bond with carbon, R1 and R2, hydrogen, hydrogen. So there is restricted rotation, that is why R2 is now shifted here. This alkene, which has two R groups on the same side. R group is nothing but alkyl group. Alkyl group can be any methyl group or ethyl group, or in the example which I have sent in your text, they have written CH3. So if they are on the same side, and if R is supposed to be, we'll select one more slide here, where if this is supposed to be, if R is CH3 with H and H, this compound is supposed to be called as cis, and how many carbons? 1, 2, 3, 4, butene. The other example was carbon having double bond which has CH3 on the opposite sides due to restricted rotation, and opposite side, that means trans butene. Cis means on same side, trans means on opposite side. And if they are on the opposite side, it is cis isomer, sorry, on same side cis isomer, on opposite sides it is trans isomer, And these are the examples for geometrical isomerism. Well, this is what I intend to explain with this video. What I'll do, I'll stop here, and in the next video I'll try to convey the method of preparation and type of reaction, if possible, along with Markovnikov's rule. Thank you.